All right, the moment you've been waiting for. Welcome to calculus. You've been trying to get to this class your whole entire life, and this is where we're going to basically start talking about calculus. So, congratulations, way to go. You're awesome. If I had like a special recording of clapping, it would sound like this. Okay, but you made it. Now, the first thing that we're going to talk about when we talk about this introduction to calculus is we're going to talk about a particular topic that's referred to as limits. Okay. Now, one of the things I want to say about when we take calculus and when we take that versus what we've been doing up till now, which is kind of based on an algebra kind of premise, is that the real main difference between calculus and algebra is that algebra is very definitive. It is what I would like to call discrete, meaning that it has specific answers to questions. It's very black and white. It's like, I want to go find f of 2, I go get f of 2, and I get the answer for it. Calculus, on the other hand, worries about other things that are interesting to talk about, and it deals with a lot of specific ideas in terms of limits of when we start to approach certain values. Now, that's going to be a new word for us to really think about here. When we approach something, we're not quite there, but we're almost there. All right. So we got to think about what's the graph doing as we get really, really close or we approach something. So this is about being close to something, not actually being there. Another thing calculus really does a good job of understanding is understanding this infinity concept. Infinity is weird, and we draw asymptotes all the times in algebra, and we've really not said much about them. But in terms of calculus, understanding what infinity does, be that it's positive or negative infinity, really does have implications in its own right. So the idea here started to help us understand and make definitive ideas about what answers should turn out to be based on something that's getting close to a specific value, but not quite there yet. Now, in terms of its use in engineering or in sciences, it really does end up answering a lot of questions that we were having problems with at the time that Leibniz and Sir Isaac Newton came up with calculus. And that was like trying to describe the size of an atom or trying to weigh an electron or understanding the idea of an angstrom. Those ideas were so small, or they could be quantified on really large levels of another concepts of science, that we really couldn't use just definitive algebra to come up with the answers for it. So we had to come up with some other methodology of getting close to the answer and feeling somewhat confident that we had come up with the right answer. Now, if some of you guys do disagree with me that I say Leibniz and Sir Isaac Newton, there's a story behind that. I truly believe that Sir Isaac Newton stole calculus from a little Polish guy named Leibniz. He wrote him some letters, and then Newton ended up publishing them. But that's history, and that's thievery, and I guess you get knighted for that. Okay, so here what we're going to do is we're going to talk about first the definition of what a limit basically means. Now, we'll read the definition, and then I'll explain to you what the individual pieces are. So a limit represents a value for a function as it is approaching a specific x value, or I'll put here domain. So we're going to have to be very clear when we talk about x as our domain and y as our range. So in general, when we say the limit of a particular function as the x gets really, really close to a specific value, then it generates what the limit's answer is. And that limit's answer is a y value that you're going to end up getting, or better yet, a range. Now, the concept that limits give you range answers is something you need to kind of put in your head. So when we read this statement, we read it as the limit of the function f of x as it approaches a specific value, in this case a, this a value in this case is infinity, it will equal the limit, whatever the answer is, in terms of its y value that you're going to end up getting. Now, What this means is you get really close to the value of a, but you still really remain unequal to that particular value, you can get a corresponding f of x that would be that would be really close to the actual limit's value. Now, the way I like to think of limits themselves is like riding a roller coaster. Okay, we all like riding roller coasters. And here's the reason why I think of it as riding like a roller coaster. Functions, when we draw them, in these particular cases, they kind of look like the bumps that you would see in a roller coaster. You're like, wee, I'm at Disneyland, way fun. Okay, that's the same kind of idea I want you to think about when you're riding on this function, is to figuring out where you're getting close to as you move along the domain of the function's roller coaster. So let's say, for instance, we wanted to find just definitive answer in terms of algebra. Now, this is an algebra problem. F of 2 is just saying, go find 2 on the domain and then go up to the function and tell me what the answer is to that function. Now, this is why it's definitively algebra, because the answer is there. You'd be like, oh, it's 3. Pretty straightforward. Now, when we read a limit, on the other hand, say we were talking about, say, that same function that we've got right here, f of x, that's our function that we're dealing with, as it approached the number 2, what would the answer be? Well, you could approach the number 2 on the domain right here on this function from 2 different directions. You could ride the roller coaster going this way, and the person that would be riding on this roller coaster going up the hill would definitely agree with you as he got closer and closer and closer to that particular domain of 2. He would be like, yeah, I'm reaching the peak, and that peak seems like I'm getting really close to, and he'd say, I'm getting close to 3. But on the other hand, another person may be riding the roller coaster another direction from the right-hand side. He looks at it from a completely different perspective. And he would be like, okay, I'm riding the roller coaster this way. And where am I going to reach to once I reach a domain of 2 as well? And he would be like, yeah, I agree. I think we're reaching the height of 3. Now, the thing about this left and right way of looking at a limit is exactly one of the fundamental ideas about limits. Limits are... when you look at a limit, you have to look at it from both ways. And those 2 ways, they have to agree that that is the answer to it. Because otherwise, if they disagree, one's shouting, no, it's over here. And the other guy's going, no, it's over here. And they can't agree what they're trying to say it's really getting close to. Now, since both of these guys agree that it's 3, the limit in this case would be the number 3. Okay? And that whole idea of kind of approaching it from either side really does simplify the idea of what a limit is saying. Now, let's try it again. Let's try the algebra sense again and see if there's really any difference. And what is f of 0? Well, if I went to 0, I'd be like, oh, f of 0 is negative 3. And if I rode this particular graph on its roller coaster, I'll be like, wee, it's headed downward. And this guy from the left-hand side of 0 would agree that he's like, all right, we're getting really, really close. As I get closer to this, I'm getting closer to negative 3 on this side. And the guy on the other side would probably agree with it in the same regard. And that the limit would be, in this case, all right, I agree with you, it's negative 3. So the limit as x would approach 0 would be the number negative 3. Now, what you're probably going to ask is, you're like, why is the limit going to be the same as the algebra discrete answer all the time? And the answer to that is no. And the reason behind that is that between these 2 functions that we both looked at right here, they were both what are considered continuous. Okay? And when things are continuous, they flow and they meet together and they don't have any breaking points in them. But that's not always the case when we talk about graphs in terms of algebra or even any kinds of math graphs. Now, you can totally take a look at number 3 right here. And the graph is what's referred to as disjoint, meaning that the answer to this graph is it's not connected like it should be. Now I'm going to do the algebra one and evaluate when f is -1. Now the closed circles and open circles start to matter now. If I say I wanted it to be at -1, you'd have to pick this one down below and say that the answer is -2. It has a definitive answer, and it's the one that's inclusive. But if I went to the limit of this function as it approached -2, I would end up getting disagreement from the left and right hand roller coaster riders. They would not agree on what the answer is. This guy would be like, yeah, the graph's getting really high. It's all the way up here, getting really close to 3. That's what the left-hand guy would say. But the right-hand one, as he approached -1 as the domain, he would be like, nah, I disagree with you. It's getting really close down here to -2. And now these two answers don't agree with one another, and therefore the limit can't be stated because it's not really getting close to anything specific. So the answer to this would be the empty set. It doesn't exist. That particular limit has no answer. Now there's an answer where you would get something for the algebra way of thinking about it, but the limit way would be completely broken. Okay? You can actually have several different circumstances, and we've seen many of these when we graph stuff in Algebra 2. For instance, this is a rational function. Now, if I was to say, what is f at -2? Well, here's the domain of -2 right here. The graph has, and we all know that's an asymptote at that particular deal. And we'd be like, well, gee, the asymptote doesn't have any answer at f of -2. It's undefined, and it doesn't have an answer at that spot. We've seen that in the past, and that's reasonable. I mean, like, we can't get to it. Now, what would the limit say about these two things? Now, as you approach this limit coming in on the left-hand side of -2, which it can be written this way. When we say we're coming in from the left, we put a little superscript up above it saying the negative of -2 coming in from the left. And that is what this symbol means. It says I'm coming in from the left. Well, the left guy would say, yeah, the graph's going way down way fast. It's headed towards -infinity. As if I keep riding that thing, I'm going to go to hell. Oh, that'd be bad. Okay, but on the other side, maybe it's a good mathematician, and he's riding the roller coaster from the right-hand side of -2, which would be -2 coming in from the positive side of it. He's headed, whoa, I've done something really right. I'm headed to positive infinity, or I'm headed to heaven. Now, here's the problem. Do the two of them agree about the limit itself as it's headed towards -2? And the answer is no, they don't agree. This one is stating, do both of you guys get the same answer? And the answer to that is the empty set. Again, they don't agree, so the limit at that particular spot doesn't exist. Okay? So we can really get some information about approaching concepts of really what you're really getting to in the end. Now, let's try a couple of these other disjoint kind of graphs. Definitely, we're going to f of 1, and that would be this domain right here at 1, and there isn't an answer there. That's an open circle, so you're like, well, it's undefined at that particular case. It happens to be a hole that's in the graph. We've seen holes before. That's okay. It's undefined at that spot. But the limit of this, is it going to follow the same suit? And the answer to that is no. The left-hand guy is going to ride onto the limit, and he's going to be like, okay, if I'm coming in from 1 from the left, he would say, hey, the answer looks like it's getting really close to a y value of 0. Now remember, all your limit answers are y values. Like, I'm following along on the domain and looking at the graph and what the y value is at that particular domain. Now, if I look at 1 coming in from the right-hand guy, he's probably going to say, yeah, I'm going to ride along this piece right here and get really close to the domain of 1. And I'm going to say, yeah, it looks like it's 0 too as well. And that would mean that the limit would be as x approaches 1, which is a both-handed concept, both of them have to agree, those two limits agree that the answer is 0. And that's because they both are standing on either side of that hole, and they're both screaming across at each other, hey, yeah, the hole is right here, buddy, and it's at 0, or 1 and 0, and that's where it's going to be located. So you can have discrepancies between your algebra sense of real defined discrete idea and your limit, which is more about approaching and closeness concept. Now let's try again. F as it is -1. Well, -1 is this domain right here, and man, that looks like an asymptote right there. So you'd be like, oh man, that's undefined, and it doesn't have an answer because it doesn't reach that. But the limit, if I was riding that roller coaster from either side, I'd be right, whoa, that guy's headed upstairs to positive infinity, and this guy from the right-hand side is headed to positive infinity, and the limit as we would approach that particular domain would be approaching positive infinity. And it's totally reasonable that a limit can be expressed as a very innocuous term, such as infinity or even negative infinity, because that asymptote is headed in that direction. So we can get some really bizarre answers when we start talking about those. Now, some things that we're going to basically talk about is like, how do you come up with an answer to the limit? Now, up above, you are really looking at a graph to make a decision on what the limit was. Now, that would be great if everything in calculus was graphed, but you know what? They're going to give you limits that look like this, and the answer is going to end up being, don't graph it, give me the limit and tell me how to figure it out. Now, let me give you, you might be given just a particular formula, or you might be given an equation that you have to come up with the limit to. Well, when you're given some kind of an equation, I like to think of this falls under what I would call the 90-10 rule. 90% of the time and 10% of the time is what was going to happen when we evaluate a limit. Now, 90% of the time, it turns out that if you just take the value that the limit is being stated as, and you just plug it in to the limit, it will generate the limit's answer, which is going to be 0. Now, I say that the 90% rule is plug it in. And it happens that 90% of the time you plug the value in, you get something nice on the other side. And that's the actual limit. Now, let me just make sure that this graph makes sense to us. The graph of 5x happens to be a line that goes through the origin like this. And if I approached it from the left and the right, it would be really what when it got close to 0? It looks like it'd be 0 because its y-intercept would be there. So the graph corresponds to the idea. Now, this is a 90% rule. Well, what would trigger a possible 10% rule? Well, sometimes when you plug stuff in, you get some really bizarre things that could possibly happen. Like you might get infinity over infinity. This is a dead giveaway that something bad has actually happened. Please don't say that answer is 1. That's not the case. Or you might even get negative infinity over negative infinity. Or you might get something that has 0 over 0. Or you get something that has a 0 in the denominator. Now, all of those are dead giveaways that there's something else going on. And you have to take a look at the 10% rule is do some other algebra. Do some algebra to figure out what you're trying to talk about. You could do algebra, or you might look at a table, or you might look at a graph to make a decision of what's going on there. Now, the ones that they want you to see here, they're saying tablize it. I'm going to try a table on this guy right here. And it turns out that the first time I try it out, I would plug in for the 90% rule as the limit approached -1. And you'll probably notice right out of the gate, I would get 1 over 0, which is undefined. Now you're like, yeah, I can't put undefined as an answer for a limit. Either a limit doesn't exist, or they agree that the answer is going to be. Now what I'm going to do is I'm going to take this graph and I'm going to put it into a table and show you how to tablize these particular values so that you can get some indication of what's going on. Now, first off, we would for sure want the function itself in the graphing calculator. So 1 divided by, make sure we're dividing by everything, x plus 1 on the bottom. Oops, I need a plus 1 there. Plus 1. And as we're probably recognizing, this is a rational function of what's going on. Now, your first shot at pushing the word table, second table, might be, like this, and it looks kind of a little bit bizarre. And here's what I'm going to have you guys do, because this is something that you haven't really played around with. Remember that when we make tables, the tables in terms of limits need to approach a specific value, and in this case, that specific value is -1. So we want to get really, really close to it and see the values of what they're doing as we get close to that value. So what I'm going to do is go into a table set, and what I'm going to say is start the table at the value that you want it to be at, which is at -1. But it's the key part is the table set. We don't want to make it so that it counts by ones, because even counting by ones is infinitely far away between 1 to 2. Okay, that's a long ways. Maybe we might want to shorten that interval to be something relatively small. Now, I usually go with either 0.1 or 0.01, use a tenth or a hundredth so that you can see what's going on in the table. Now, if I go back to the table, you'll probably recognize an error. And we expected that because that's what the 90% rule is, something wrong at that particular spot. Now, when we look at the table itself, and I'm going to see if I can drag that on here. Will it drag? It won't do it. Okay. That table has some numbers up above -1, which are on the left-hand side, and we have numbers that are on the other side of -1, and we can see what they're doing. Now, let's go to the left first. So if I went to the left of this particular deal, here's -1, and I went to the left-hand side of it, or more negative, these guys are getting -33, -50, -100. It's getting bigger, or excuse me, it's getting really, really small. It's getting closer to -100 and probably -200 if I got even closer. So this guy is probably headed towards -infinity. So it's going down. Versus on the other side, the positive side of this, or the plus side, I would say that the graph is getting bigger on the other side. Plus, it's going to 100, maybe even one more than that would be 200, and so forth. This guy's headed to positive infinity. Now, here's the deal. Do the left and the right agree? And in this particular case, they don't. So the answer is no, they don't agree. So the key is, what's the answer to both of the limits themselves? And the answer to that is it doesn't exist. The two of them can't come to a consensus, and the limit would be unattainable. Okay, so there's a little bit more to something like that when you hit the 10% rule. Okay, here's another example right here. First, I'll try the 90% rule and see what I end up getting. Well, as soon as I try the 90% rule, I'm going to get a divide by 0. And tan of 0, for those of you who've forgotten your trig, let's take a look at what tan of 0 is supposed to be. Maybe my mode should be in radians. That makes sense. And I'm going to go tan of 0. And if you've forgotten this, it's because your brain is stopped. And the tan of 0 is 0. Okay, 0 over 0. That is an indicator that there's something else going on. You're like, oh, man, 10% rule. There's got to be something else I've got to do. So let's take a look at the table and see if we can figure out what's actually happening with x's and y's as they get close to 0. Now, go to our table. Let's go y equals. And instead of that one right there, we're going to put in tan of x. Close that bad boy. Divide by x. And we're going to go to the table again. And before I even push table, I might just table set this thing right out of the gate and be like, okay, I want it to start at 0 because that's the closest. We'll go by hundreds. That seems reasonable. And now I can go to my table and see what's happening. Now, do the left and the right agree what's going on? On the negative side of this guy, it's headed to 1. And on the positive side of it, it's headed to 1 as well, too. So the left and the right guys agree that we are approaching really close to the number 1, and ultimately this limit's answer would be 1. Okay, do not think that 0, it's just because 0 divided by 0 seems like it should be 1 to you. That isn't why it is that way. It's because the graph is doing such a thing. Okay, now tables can really be helpful. Graphs can be really helpful. Later we'll discuss some algebra techniques that can be useful too as well. But you got to make sure you understand that you're talking about a domain that's talking about both. Which way are we coming in from? Now, when we do one that has a inequality sense to it, it's like it's turning on a light switch. We have to really think about what is it doing as x approaches from the negative side. And if I was coming in from the negative side, which one of these two functions would be turned on? Well, if I'm coming in from the left, I'm coming in from the negative side of 1, and that would mean that this one would be the one that would get turned on. And if I want to evaluate that function, well, heck, I'm going to use the 90% rule and see what it says. Well, the 90% rule plugging 1 in there would mean that the limit coming from the left is 2. But if I said the limit was coming in from the other side, coming into 1 from the right-hand side, that would flip on a different part of the function because it's on the other side of 1. It's on the positive side of it, which would make the x's greater than or equal to 1 in this particular regard. Now, if I plugged in 1 in that, I'd get 0. Now, here's the part. Do the two left and right functions agree or not? And the answer is no, they don't agree on this. So the answer to the both concept over here would be that the limit doesn't exist. And it would really mean that those two particular graphs, they are not continuous. They don't connect at that spot. There is a hole there, a break, and then the graph starts again from another spot. So where limits don't exist can be a very clear indicator of discontinuity in a graph. So maybe that might be a way of thinking about limits in reverse. Okay? Now, again, remember, the key to understanding a limit is the first idea that it is about an approaching concept. It's not about actually being on that domain. It's about getting really super close to it. And if you're coming in from the right and you're coming in from the left, they better be equal to each other. Otherwise, the limit itself does not exist. And if they agree, they didn't exist. If it doesn't exist. Now, that's the both concept. And remember that when we say something like this to the negative, that's left. And when we say something like this, that's right. And if we say just as x approaches 1, that's both. Okay, so there's a syntax concept here that you really need to be aware of. And it says here, if they're not equal, it doesn't exist. It's an empty set, and it doesn't make a chance for it to work. Okay, now, one of the things limits work really well on in helping you understand is specifically and the hardest ones that we've always struggled with in algebra all along. And you wonder why your algebra teacher made such a big freaking deal of it. And that is because when you're starting to deal with functions that are pieced together like this, like a Frankenstein graph or a piecewise function, then limits really start to get involved in the whole entire thing. And you can see, like, man, I'm on the limit of this, limit of that. Maybe they won't agree, and so forth. Now, what I'm going to do is I'm going to pause the video, and miraculously, this graph will show up in the right. And I want you to check, make sure I've done my graph correctly. I'll go over it. And then we will talk about the limits and function notations that are down below. All right, here we go. Pause. And pazzow! I'm going to use blam. Blam, like we're on a Batman movie. All right, here we go. Let's see if I did this actually right. Okay, first off, I graphed the starting part of this from -1 down in that orange color, and it was supposed to be at a level of 1. And then I went to the green one. When it was actually -1, it's 2, so I went put a green dot there. Blue from -1 to 0 inclusive, it's a slope of -1. So that went down and it included that spot. Okay. Then I went to pink and it started at a y-intercept of 2 and had a slope of 1. So went up 1 over 1, but it didn't include either one. So that was an open circle there. And then purple was at 1 is equal to 1. So that's purple dot. That's that one. And then I went to +7. Now I put a little X up here. Here's showing the 1, 2, 3, 4, 5, 6, 7. That's the y-intercept. Down 4, 1, 2, 3, 4 over 1. Fill it in because now I think that should be an open circle. All right. I'm going to put that as an open circle. Open circle. Because I don't think it includes it because it doesn't have the bar here. Then down 4, 1, 2, 3, 4 over 1. And that should have been an open circle right there. But ultimately it gets filled in because this one has a bar underneath and it continues from that particular spot. So I think my only mistake is that should be an open circle at that particular spot. Let's keep that in mind. I'm going to point at it. Open. All right. Now, I think I got this guy right. And again, piecewise functions, you got to be systematic. I color-coded it, so it made it a little bit easier for us to look at. Sorry that line is a little crooked because it's not straight. All right, now we're going to do this first one right here, which is going to be at -1. And I'm going to be like, okay, I just got to go evaluate good old-fashioned algebra, and I want to do what's the answer when it's -1 is the domain. Now, it's the only one that's got to be filled in, and it would have to be this green spot right here, which would be the number 2. Ta-da! That was super easy. Now, if I start thinking about the limits, though, at that -1, I'm going to write, hey, what's the limit as it approaches -1? Now, as soon as I write it like that, I'm talking about both. But if I want to really understand both, I probably should understand what the left is going to say and what the right is going to end up saying. Because if the two of them don't agree, then the limit won't be possible. Now, if I was coming in on this roller coaster from the left-hand side of -1, I'd be on the orange line. Here I come, here I come, here I come on the roller coaster towards -1. I'm not there yet. I'm approaching. I would say the answer from the left is 1 because that's what the level of the range is. But if I was riding this roller coaster from the right-hand side, I'd be on this blue line coming in from the right-hand side, and I would disagree that it's headed to a y range of 2. In this case, the two answers for the left and right domain don't agree, and the answer for the both is it doesn't exist. It's disjoint at that spot. That's why it's not going to have a limit there. Okay, let's keep trying. Next one, f of 0. Ooh, f of 0, blue dot. Must be that guy right there. Answer is 1. All right, great. Now, let's see if we can find out what the limit is as it approaches 0. But I'd have to think about what is it going to say as it approaches it from the left and what it says about it when it approaches it from the right. Well, if I approach the graph from the left-hand side of 0, I would be riding on this blue line from the left-hand side, and I'd be like, wee, I'm coming down. I'm on the number 1. Okay? But if I was riding it from the right-hand side, I would be on which graph as I was coming towards 0? I'd be on the pink graph. This pink graph is coming down, and it says that the answer is going to be 2. And that answer would be the number 2. Again, do the limits agree? Nope. Disjoint location, empty set. It does not exist. Okay? Let's try again. F of 1. Ooh, f of 1. Yes, that answer is 1 because it's a purple dot. Now remember, we had to say that that guy was open. If I wanted to find the limit as it approached 1 or both, I'd have to think of 1 from the left and 1 from the right. And what two numbers would I end up getting? Well, the left-hand guy would be riding on the pink graph. Woohoo! We're up to 3. I love it. We're on the right-hand side of 1, riding on the orange graph, and he agrees that the answer is 3. And look, they agree because they approach the same number, not because of what the value is at that spot of domain, but what we're getting close to. Answer for the both domain, 3. And here's a funky thing. The limit is 3, but the actual answer algebra-wise is 1. Yeah, they don't have to agree, people. This is about approaching things and not about what is actually on that location. So it's about more agreement. What do they agree we're getting really close to? Let's try 2. F of 2. F of 2 is -1. All right, looking good. And the limit as x approaches 2, or x approaches 2 from the left and from the right, what answers would we end up getting? Well, if I approach 2 from the left, I'd be on orange and say, oh, that's -1. And if I approached it from the right, I'd be on this light blue one, and that would be, oh, -1. And the limit would be -1 because they agree with each other. And that would be a circumstance where you could see that the algebra and the calculus limits do agree on certain things. That's a continuous location. Now, you're going to be asked to do some of this kind of stuff tonight on your Math Excel. Give it a shot. You guys are totally capable of doing all this. And if you struggle in any way, shape, or form, watch the video again or check out Miss Merzak's homework help tips, and they can really help you get through the Math Excel with a lot of success. Hey guys, we're doing calculus. Woohoo! It's the train to Smart Town.